So when does one do this between subjects ANOVA? Well, you use it when you have one nominal or ordinal between subjects independent variable, and that variable has 3 or more levels. And you've got a dV that's measured on an interval or ratio scale. So you've got an IV that's 3 or more levels, and you've got a dV that's interval or ratio. So it's basically the same thing as an independent t-test, but when you have 3 or more groups. So you can actually use this when you just have 2 groups, but why would you use a t-test? It's easier. So it's sort of the generalization of independent t to 3 or more groups. So some examples. If you want to compare the number of items correctly answered on the DV written test across 4 different types of instruction, classroom instruction, some sort of like CD-ROM home study course, a paper-based workbook home study course, and an internet home study course. What is the dependent variable here? Your dependent variable is the number of items correctly answered on DV's written test, so it's their test score. That can range from 0 to whatever it is, 46, I think. And you're going to compare it across folks who are in 4 different conditions. Some people take the classroom, some people take this, some people take that. So this is a between groups design. It's different people in the different courses, and an interval or ratio dV. Another example, let's say you just want to compare self-esteem scores of Chinese immigrants who are first, second, or third generation in the United States. What is the dV? Well, it's self-esteem scores. And again, in this class, we have an agreement based on the skills measurement lecture that anything psychological in nature that we measure is at least interval. So we've got an interval dV. And what are we going to be comparing that dV between? Well, everyone's a Chinese immigrant in here, so that's a constant. But what varies is whether they're first, second, or third generation in the United States. And so that is 3 groups, 3 levels, I guess, generation, and it's got 3 levels, and so you got a 3-level independent variable. How about to study the effects of caffeine on words recalled, where each participant receives one of the following caffeine levels, either low, medium, or high caffeine. dV is words recalled, which is ratio, but close enough to interval ratio. And the independent variable is 3 levels, low, medium, or high. Each person only gets one of those, so it is indeed a between groups design with 3 or more levels and an interval/ratio dV. That is between subjects ANOVA. Finally, let's say you wanted to look at the effects of test difficulty on state anxiety. This is going to be the one we analyze later too. So each participant receives one of the following test difficult levels, low, medium, or high. So again, we've got a 3-level independent variable, whether the initial test they take is low difficulty, medium difficulty, or high difficulty. And the dV we're measuring is state anxiety, psych measure, so it's interval or ratio. So let's talk about what things are assumptions for you to be able to do a one-way between subjects ANOVA. Besides the things we talked about, the data already, you've got an interval or ratio dV and an independent variable that's nominal/ordinal with 3 or more levels. These are those statistical assumptions, things that need to be true for the test to give you an accurate result. That is for you to have good statistical validity. So number 1 is independence. So the participants in each level of the independent variable should be independent from each other. Shouldn't be correlated, shouldn't be paired, shouldn't be the same people, shouldn't be siblings, shouldn't be partners, that sort of thing. They're just completely different people, except for the fact they're in your study, and maybe they share some characteristic of interest. You're just doing a study on all men, for example. They're not related, and they're not the same people. So really, that's just saying between subjects design. If you violated that, you're using the right type of ANOVA. We'll learn about the right type of ANOVA for that design, dependent design next week. So the next assumption is the same assumption as it was for independent sample t-test, except that you've got more than 2 groups now. And that is that the dV is approximately normally distributed for each IV level. So if you look at the shape of scores for each of your 3 or more levels on the dV, you'll see that it's approximately normal. So guess how we test that? we look at the skewness coefficient. So in the explore procedure, you would run the skewness coefficient for each level of the independent variable looking at the dv, and you expect that skewness coefficient to have an absolute value that is less than 2. Normal enough, this assumption's met. If any one of them is 2 or bigger, you got a problem. Except that ANOVA is robust to deviations from normality. So unless like you've got extreme skew. So what does it mean to say it's robust? Robust means that you can still get good results out of the study even when the normality assumption is somewhat violated. So it's robust, particularly again if you got big sample sizes and they're equal, like independent t. So down here at the bottom we have 4 different distributions. So think of these as the dB scores for 4 different groups. Each of them is normally distributed. There's a different problem across the 4 different groups scores there, and that is the spread of them differs. So we're going to have a problem with heterogeneity when we get to that assumption. Whereas the ones on the right over here are very, very skewed. These are clearly all right skewed, and severely so. This would be one of those big violations that you might have a problem with your ANOVA and have to do a backup test. The third assumption is homogeneity of variances. It's the same as it was for independent t, except there's more than 2 groups now. So it's that the dV variances are approximately equal across all the levels. So the spread of scores is approximately the same for all levels of the independent variable for the dV. So here are 2 different distributions. I know it's supposed to be 3 or more, but this was the best example I could find of this. Note that S, that's a variance, well, actually it's standard deviation. For the top one, it's kind of lower and wider. The distribution that's S2 is more peaked, and we call that leptokurtic. Actually, this might be a problem with heterogeneous variances because the ones on the top are more spread out than the ones at the bottom, and you might find you end up violating the assumptions if you get a situation like that. Or was shown on the slide, the prior slide, on the left side. So we test this again using Levene's homogeneity variance test in SPSS. I click a box, it spits it out. The null hypothesis of this test is a little unusual, so point it out because maybe it helps you understand a little better. It's that the variance of group 1 is equal to the variance of group 2 is equal to the variance of group 3, and you just kind of keep going. It's group 4 if you have a group 4, group 5 if you have a group 5. That's what S little n means. So the null hypothesis is that the variances are equal, that is, they are homogeneous. And this is why this is that test where you actually don't want it to be less than 0.05. And so if Levene's sig is greater than 0.05, you retain that null hypothesis, right? So you say, yes, the variances are, give or take an extra red skittle, basically not different from each other, basically the same. They're homogeneous. If your Levene sig is less than 0.05, you got a problem. You have violated this assumption. The variances aren't all equal to each other, and you got to do something about that. So what do you do about it if you have a homogeneity variance violation of this assumption? Well, you're going to have type 1 error inflation. That is sort of what occurs when you violate the assumption. So you think you're using 0.05, but when you violate this assumption and continue to use ANOVA, your type 1 error rate is inflated. It's something bigger than 0.05. And so we call that type 1 error inflation. So if you violate the homogeneity variance assumption, there's 2 things you could do really. One is you can implement a more stringent alpha level. So instead of using 0.05, you could counter that type 1 error inflation by using a more stringent alpha level, say 0.01. It reduces your power though. The other thing you can do is use the Weedwhacker backup test for one-way between subjects ANOVA. If you look at the matrix O statistical test, look what is above one-way between subjects ANOVA in the ordinal row, you'll see that is called the Kruskal-Wallis test. So you can always use that. That's your backup test. Like if your normality is severely violated, that's your backup test as well. So you just select homogeneity variance test in the options button. when you're selecting things in SPSS for your one-way ANOVA, that's going to get you this test as part of your output. So it's not automatically printed like it was for independent T. So why not just run a bunch of independent t-tests, right? Like, why learn this new thing? Why don't I just run a bunch of t-tests, and I already know how to do those from last week and get this over with? Good question. So here's an example. So let's say Between-Subjects IV has just 3 levels, the simplest form of this, A, B, and C, and you want to compare them all to each other. So you want to be able to say this one's higher than that one, and that one's higher than that one, and that one's higher than that one, or not, whatever your hypotheses happen to be. You would have to compute 3 different tests to do all those pairwise comparisons. So what are they? Oh, sorry. In each pairwise comparison, that is mean-to-mean comparison, you're going to be evaluating the statistical significance at an alpha level of 0.05. Well, what is an alpha level of 0.05? That is your likelihood of making a type 1 error, right? So there's our 3 levels, A, B, and C. Let's look at our 3 tests. We want to compare A to B. That's an alpha of 0.05, so we got a 5% chance of making a type 1 error there. We also need to compare A to C because we're going to do all possible one-to-one comparisons here. That's also a 5% chance of making a type 1 error. And finally, B to C, also another 5% chance of making a type 1 error. And it turns out these things are additive. So even though each test you only had a 5% chance of making a type 1 error, added across the 3 tests, you actually have a 15% chance because it's 0.05 plus 0.05 plus 0.05. So you got a 50% chance of making a type 1 error. So this is, again, type 1 error inflation because you're doing multiple tests on your data. The data are related. It increases your type 1 error rate, and that's bad. You don't want a 15% chance of rejecting the null when you shouldn't. That is a type 1 error. So that is called your family-wise alpha level, or alpha family-wise. And for this study, it is inflated, meaning that it's higher than what you think it is, your alpha of 0.05. It's actually 0.05 times 3. So this is why you don't want to do 3 independent samples t-tests. You want to do this ANOVA, because I'll show you why in a sec. So the hypotheses for Between-Subjects ANOVA particularly is, I think you'll like this. So the null hypothesis is always that the means of all the groups are equal. So if it's 3 groups, it's that they're all equal. If it's 4 groups, they're all equal. It's always mean of 1 equals mean of 2 equals mean of 3 equals ... like that. So you x of n, by the way, just means keep going. Your alternative hypothesis is always that the means are not all equal to each other. So let me repeat that. So the null is that the mean for the DV for the groups are all equal to each other. So x bar 1 equals x bar 2 equals x bar 3, etc. The alternative is that they're not all equal to each other. There is no like x bar 1 is less than x bar 2, which is greater than x bar 3. It's just equal and not equal. So again, n just means keep going. So if you got 7 levels, you just keep doing these little x bar things out in space. So you get to x bar 7. So the implication here, and this is how it saves you from type 1 error inflation, is that what it tests is many things at one time. So we call that an omnibus test. Specifically, it's always a two-tailed test. It's always, you can have directional hypotheses about how individual means will differ from each other, but this initial test that ANOVA does, this omnibus test, compares all the levels to all the other levels at one time. So in this example, the ANOVA will not inflate your type 1 error rate because it tests whether any of the 3 levels differ from each other at one time rather than doing separate tests. So it's just 1.05 rather than 3 separate ones. So again, let me say it one more time. It tests at the same time that all the levels are equal to each other, or they're not all equal to each other. So it doesn't test like, mean of 1 is greater than 2, which is equal to 3 or anything like that. It's always, these null and alternative hypotheses are always written the same as equal and not equal. And your ANOVA will be statistically significant if any group differs from any other group. So that's how it saves your type 1 error inflation. So, and that's what I say here. The omnibus ANOVA will be statistically significant if any of the IV levels differ from each other on the mean DV scores. All right, so there's a decision rule for a one-way between subjects ANOVA, like all the stats we do. It's pretty straightforward. If the ANOVA sig is less than 0.05, you're going to reject the null. So it's actually even easier than independent samples T, because independent samples T could have one and two-tailed hypotheses. This is always two-tailed. So if the sig for your ANOVA is less than 0.05, you will reject the null hypothesis that the means are all equal to each other, because that means they're not all equal to each other. There's at least one difference. If your ANOVA sig is greater than 0.05, you will always retain your null. That is, except for just chance variation, the mean scores of all the groups are equal to each other. There's no difference between any of the groups, any of the levels, whatever. So when you reject the omnibus ANOVA null hypothesis, all you know is, okay, the level or group means are not all equal to each other on the DV, but you don't know who differs from who. So in order to find out exactly which levels differ from which levels, you have to do a follow-up test called a post-hoc test to determine which specific IV levels differ from each other on the DV. So post-hoc tests, for example, will tell you, and that's a guy named Tukey we'll talk about in a sec, whether A differs from B, whether A differs from C, and whether B differs from C. So it's going to do all of these pairwise comparisons and tell you, now that you've rejected the null, you know there's at least one of these things is a difference. Could be all of them, could be two of them. It's going to tell you exactly where those differences are. So because rejecting the null only tells you that the IV groups or levels differ, at least one differs from another, that is, they're not all equal to each other on the DV, you got to run additional analyses to determine exactly which of the levels groups differs from each other. Is it just one from one other, or do they all differ? You got to figure it out. So those tests again are called post-hoc tests, and they give you pairwise comparisons of all the IV level means. And the one, we're just going to use one in this class, just keep it simple. It's called Tukey. It's the Tukey's honestly significant difference test. It's a post-hoc test. I'll just call it Tukey. And so post-hoc tests, even though they're doing these mean-to-mean comparisons, also manage to keep your family-wise type 1 error rate at 0.05, your stated alpha level. It's in the way they're calculated that it does it. So that is Tukey on the left, and that's Turkey on the right, and that's how you remember it. Normally, in the classroom portion of this course, we're right by Thanksgiving each year, so it kind of works really well. But note that you only do the Tukey post-hoc tests, or at least you only look at them, if the omnibus ANOVA was statistically significant. So if in that prior step where you're looking at the ANOVA, the sig was greater than 0.05, you don't even look at your Tukeys. You may ran them, but you don't want to look at them. You only look at them if the sig for the overall ANOVA was less than 0.05. There is a measure of effect size. It's not but squared this week. It is eta squared. So it's defined as the sum of squares between divided by the sum of squares total, which you're like, what the heck are those? Well, I'm going to tell you. So SS is sum of squares. The full name is sum of squared deviations from the mean. I'm not going to ask you about that. But these sum of squares, they just come from your outputs. You're just dividing one number by another number, and to get this, it's right there on the output. And just like every other measure of effect size, it tells you the proportion of variability in the DV that is accounted for by the IV. So what proportion of variability can be accounted for by which group people were in. So this ain't shocking at all. There's APA format of exactly how you have to report the results. So just like there was R for correlation, T for t-tests, there's going to be A for ANOVA, right? No, they used F because the guy who invented it, his name was Fisher. So this is me being sarcastic. So this is the general form, and F with the degrees of freedom between, comma, degrees of freedom within is equal to the actual ANOVA F value to 2 decimal places. Then you'll do the usual P less than or greater than 0.05, and then eta squared is calculated as shown above using that formula. So everything but eta squared comes straight from your SPSS output. All right, that is the background. Let's go ahead and run one of these between subjects ANOVAs. The question we're going to ask is, does test difficulty affect state anxiety? So 90 people in the study are randomly assigned to take a test of varying difficulty. We're going to measure their state anxiety levels after they take that test. The independent variable is the difficulty level of the test, and we somehow came up with a operational definition of a low, moderate, and high difficulty test. And what we're going to do is, after they take their respective tests, and it's between subjects design because we randomly assign participants to one of those types of tests, we're going to measure their state anxiety level. And we're going to use the State Trait Anxiety Inventory to do that, the STAI. So this is what the data setup looks like in SPSS. It is the same as that for independent samples t-test. You have one column that is for the independent variable, and so low, moderates, and highs, but you guys know there's numbers behind those, like 1, 2, and 3, or 0, 1, and 2, whatever. And then there's a second column that is for the dependent variable, and that is their state anxiety levels. This is the first thing that pops out on the SPSS output. It's your descriptives table. There's all sorts of stuff in here. Noise, really. But the important things are, you can see there's 30 in each group. There's 30 low, moderate, and high, 90 overall. You get means, standard deviations for each of the groups, and a bunch of other stuff. So the means and standard deviations you're going to need for the APA write-up. When you do this, this is where you get your means and standard deviations for what we sort of refer to as Table 1, which is like in every research study always is Table 1, means and standard deviations of blah, blah, blah. So take a look at the means for a sec before you keep going. So note that the low group, the first row there, had a mean anxiety of 35.67. The moderate difficulty test group had a mean anxiety of 46. So higher, right? A lot higher, it looks like it, 0.47. Then the high difficulty group, the mean actually, if anything, goes down a little bit, right, to 41. So it's the lowest, then it kind of goes up, and then it seems to go down a little. But the question is, are these real differences, or is this just chance differences? That's why we take the class. That's why we have to actually run the stat. So the next thing that appears on the output is the test of the homogeneity of variances assumption. This is that assumption that ANOVA is not robust to. That is, if you violate it, it really messes up the results pretty badly. And so you do want to test it. So it's called the test of homogeneity of variances. It's a big table. On the left down here, we have an example for at least two groups, what heterogeneous variances would look like on the left. One's way more peaked, and the scores aren't as spread out, and then there's sort of a flatter one that is platykurtic. So that would be an example where you probably get a violation of the homogeneity of variances assumption. The ones on the right overlap a lot more, right? So they're not exactly the same, but they're probably close enough, and that's what we're talking about here with this test. So is the homogeneity of variances assumption met or violated? So there's lots of rows in this table, so we're going to use the based on mean row. And our decision rule, there's our sig value, 0.815, is if based on mean sig is greater than 0.05, our homogeneity assumption is met. Okay, so we've met the assumption. However, if our based on mean sig is less than 0.05, we have violated the homogeneity of variance assumption. It means we got problems. So is 0.815 greater than 0.05 or less than 0.05? Well, it is clearly greater than, so what's that mean? First part of the decision rule, homogeneity assumption met. So yes, 0.815 is greater than 0.05, we have met the homogeneity variance assumption. So on the left, the results basically tell us that the variances are close enough to equal. Or what do we say for normality? Good enough. So we don't have that. We've got the happy face one. So now we can go ahead and look at the actual ANOVA omnibus comparison of the group means. This is the fun part. This is where we're actually looking at whether test difficulty affected their anxiety. All right, so this is going to be the omnibus test of the actual anxiety means. It's not surprisingly called ANOVA, and you can see there's a couple rows in there. There's between groups, within groups, and a row called total. and there is one sig value. So can we reject the null that the anxiety means are all equal across test difficulty levels? So I guess, again, this is an omnibus hypothesis that compares all three levels to each other at the same time, and if anyone differs, that sig will be less than 0.05. If none of them differ, sig is going to be greater than 0.05. So there is the sig. Our decision rule is as follows. If ANOVA sig is less than 0.05, reject the null. However, if your ANOVA sig is greater than 0.05, you retain the null. So the top one means at least one group differs from each other. The bottom one means nope, no difference, no anxiety between the groups. None of them differed from each other. So what is ours? We've got 0.000. That is definitely less than 0.05. So we will reject the null hypothesis because indeed 000 is less than 0.05. So what's that mean? They tell us that the anxiety means are not all equal for the three test difficulty levels. So there's at least one difference. So ANOVA, again, is an omnibus test. So all we know when we reject this omnibus null hypothesis is that at least one anxiety mean is different from at least one of the others across the three test difficulty levels. So it could be they all differ, but at least one does. That's all we know at this point. So is it, low to moderate, moderate to high, low to high, all from each other? We don't know. So what do we have to do? We got to go one more step. We have to now do our Tukey post-hoc tests to determine specifically which means differ from each other's. And they'll give us those one-to-one comparisons that tell us which ones differ exactly from each other. Okay, so at least one of the means differs from at least one of the others. Let's figure it out. Let's do our Tukey. So for our Tukey test, we're going to use an alpha of 0.05 again. Turkey. There's the means that appeared on the output. I just re-put them here to make our lives a little bit easier. And this is what the results of a Tukey multiple comparison test look like. And it's kind of a wreck. There's how many rows? 1, 2, 3, 4, 5, 6 rows. So why is there 6 rows if for 3 groups there's only 3 possible unique comparisons? Good question. So yes, SPSS prints 6 pairwise comparisons, but in reality there are only 3 of them. And the reason is SPSS does like low versus moderate, but then it'll go ahead and do moderate versus low. So it's redundant. So you got to find the 3 unique one-to-one comparisons in here and ignore the rest. So I'm actually going to line them out for you. We don't need that one because we're already doing low to moderate in the first row, so we don't need to look at moderate to low. We don't need that one because we are in the second row looking at low to high compared to high, so we don't have to then look at high compared to low. And finally, in the middle here, where it's not read out, you've got a moderate to low. That's the same as, moderate to high. That's the same as high to moderate, so we don't need to look at that twice. So those are your 3 unique comparisons: low versus moderate, low versus high, and moderate versus high test difficulty. And what we're looking at is the anxiety means. So let's check out the first one, low difficulty versus moderate difficulty. Where is that? Well, that is the first row in the table. On the left it shows low, on the next column it shows moderate. Those are the 2 levels being compared. And note that there is a sig value. There is that sig value is 0. We're going to use alpha of 0.05. So is there a difference between the low and moderate difficulty? Is there a difference in anxiety between those who got the low and moderate difficulty test? You bet. There it is. I love when it's 0. So look at the means on the left. So the low group had an average of 35.67 anxiety. The moderate group had an average of 46.47 anxiety. This test tells you those 2 things are really different. It's not just a chance difference. So who was more anxious? Well, the low, or who was less anxious, however you like it, I would say the low was less anxious at 35.67 than those who got the moderate difficulty test. And there you go, low less than moderate. That is, the anxiety levels of those who got the low difficulty test was lower than those who got the moderate difficulty test. All right, next one is low versus high. So that is the second row in the table. Again, you got low on the left and high in the second column. There's a sig value for that. There it is, 0.008. Is that less than 0.05? Yeah, right? So 0.008 is 8 times out of 1,000. That's less than 5 times out of 100. Or just simply 0.008 is less than 0.05. So those who took the low difficulty test differed from those who took the high difficulty test in their anxiety. What would you tell grandma? That's not enough. They just differed. So you look at the means over there. So low was 35.67, high was 41.7. So those two things are different. Who was, more or less anxious, however you want to say it. To keep things the same as the first one, I'd say the low at 35.67 difficulty test people had lower anxiety than those who took the high difficulty test. And our final one-to-one comparison that's unique is moderate versus high difficulty. That's the only other row that doesn't have a red line through it. There's their sig value. Is 0.046 less than 0.05? I mean, technically, yeah. So it barely, but it is, right? 0.046 is less than 0.05. Not by much, but it is. So those who took the moderate difficulty test do differ from those who took the high difficulty test in their anxiety level. So look at the two means. It's 46.47 versus 41.70. So who was higher? Who was more anxious? Well, it's the 46, right? The moderate group had a higher level of anxiety. So sort of interestingly, there wasn't this sort of linear, just going in one direction increase in anxiety. The moderate group was actually more anxious than the high difficulty group. So here's sort of how you summarize it for grandma. Overall, those with low difficulty test, I guess, were less anxious than those who got a moderate or high difficulty test. But the moderate difficulty test was more anxious. They were more anxious than those who got the high difficulty test. So again, low was lower than moderate or high. How do you know that? Well, we know low versus moderate was significant, low versus high was significant, and looking at the means, they are the lowest mean. And then for the second part of that sentence, moderate difficulty was more anxious than high. Again, we know that the red boxes that are highlighted, moderate differed from high in anxiety. And who's higher? Moderate, right? Moderate was 46.47 and high was 41.70. So here are our sort of a representation of those three means. We've got low, moderate, and high. Each one of these was significantly different from each other. And you get a means plot with ANOVA, which I really dig because I'm really visual. I don't like looking at the means. So if that last slide you're like lost, you get a picture. So I enjoy this more. You can get a means plot. So there are the three means that are plotted. So the up and down axis is mean, anxiety, and you get three groups: low, moderate, and high difficulty test. And you know each of these means differs from each of the others. So let's sort of put them in order. So those who got the low difficulty tests, you can see at the bottom there, they were the least anxious. Those who got the moderate difficulty test were the most anxious. And those who got the high difficulty test were somewhere between the low and moderates, really, right? So you got least anxious for the low difficulty, most anxious for the moderate, and then those who got the high difficulty test are somewhere in between those two, but significantly different from them both. So a quick summary: those who took the moderate difficulty test were the most anxious. Those who took the high difficulty test were the next most anxious, right? And then those who took the low difficulty test were the least anxious. And you could have said it the other way, right? You could have said the lowest anxiety was the low difficulty. Next lowest was the high difficulty test, and then the highest was the moderate difficulty test. So it's kind of an interesting effect. It's a real effect here. Anxiety did not increase in one direction. Monotonically is the word for that. As a function of test difficulty, it went up and then it kind of dropped a little bit. Or maybe they just said, this is impossible. I'm not going to be anxious about this. It's obviously stupid. Something like that. So let's calculate our measure of effect size, our eta squared. Sum of squares between divided by sum of squares total. You can see there are the top two lines. You've got between, then you got within, and at the bottom you got total. So we're going to divide in that sum of squares column the top number, 1757.622. We'll divide it by 6818.056. And that's going to tell us the proportion of variability and anxiety that can be accounted for by which test difficulty. So there it is, all filled in. You get 0.2578, which is rounded. Following the rounding rules is about 0.26. If you think of that as a percent, it's about 26% of the variability. And so those are where those two numbers come from to go in the formula for eta squared. 26% of the variability in state anxiety is accounted for by the test difficulty level. And APA format. There's the general form of it again, where we got to fill in all the info. There it is, all filled in with the info from the table above plus eta squared. You've got an F with 2 and 87 degrees of freedom was equal to 15.11. The sig value was zeros, that was less than 0.05, so we do P less than 0.05. And then finally, our eta squared comes from our little hand calculation up above is 0.26. So that is how you would report this in APA format if you reported it in a sentence. So if you think about your regression analysis, you had one of these. I just kind of told you where to get the stuff. I didn't tell you what you were doing. That was an ANOVA. But it turns out most ANOVAs are reported in a table, not in the text. So that regression assignment was the exception. So let me show you how to do that, and we're done. So in ANOVA summary table, you just copy the numbers to the SPSS output table that come from here, plus eta squared, and you got to put it into this sort of format here, APA. So each one of these numbers you will replace in the APA template with numbers from your output. So that's just sort of barfing nothing. Just says bleh, put it all in there. Note that one of the interesting things that happens is there is a column for sum of squares. There's a column for degrees of freedom, and they just come right from that table above. Same thing with mean square. The F value is 15.11, but see that little star there? That's what happens to the sig value. So you don't actually put a sig column. If the sig is less than 0.05, you put a little asterisk on the F value. And then if you look below the table, you see that that indicates that the sig, or the P, was less than 0.05. And then the final column is just eta squared, which comes from your little hand calculation, and we are done.